Hello everyone, my name is Alfredo Jimenez, and I am currently pursuing a master's degree in chemical sciences at the Universidad Autónoma Metropolitana, Unidad Iztapalapa, in Mexico. Today, I am going to present the research work I have developed as part of my thesis entitled Luminescent Properties of Hafnia-Ln Ether, Materials, Synthesis, Characterization, and Study of their Emission Response. Project Overview. This study focuses on the synthesis and analysis of hafnium oxide, HFOO, nanocrystals doped with trivalent lanthanide complexes, EUNCE, using a sol-gel synthesis route. The materials studied are HFO, HEUA, HFO diet IT, and HFO diet. The motivation behind this work lies in the optical and electronic properties of lanthanide-doped metal oxides, which make them attractive candidates for various technological applications such as catalysis, lighting systems, photovoltaics, thermographic sensors, and even bioimaging. Hafnia is known for its chemical stability, high refractive index, and wide band gap, which make it a promising host material. Experimental procedure. The synthesis was carried out via a sol-gel method, following the metal salts route. Hafnium chloride, HFL, was used as the hafnium source, and lanthanide dopants were introduced as beta-ditonate complexes. Specifically, tris, acetylastinate europium III, tris, acetylastinate gadolinium III, and tris, acetylacetyl. As illustrated in Figure 1 of the poster, the precursors were dissolved in ethanol and mixed under a nitrogen atmosphere at 600 rpm for 2 hours. After that, ammonium hydroxide was added to catalyze the sol-gel reaction. The resulting gel was washed with deionized water, dried and thermally treated at 2 different temperatures, 800 degrees C, and evaluate the effect of temperature on structural and optical properties. Characterization techniques. The materials were characterized by using the following techniques: X-ray diffraction, XRD, for crystal structure and phase identification; transmission electron microscopy, TM, for morphology and microstructure; diffuse reflectance spectroscopy, DRS, for band gap determination; photoluminescence spectroscopy, PL, to evaluate the emission properties. Results and discussion. Let's go through the main findings. TEM analysis, as shown in Figure 2, revealed that the nanocrystals obtained at 800 degrees C had non-spherical morphologies, displaying well-defined polygonal facets. The SAID patterns confirmed the monoclinic HFO phase with characteristic Miller indices such as 111, 200, and 1. The average particle size ranged from 24 to 45 nanometers, depending on the dopant and calcination temperature, as summarized in Table 1. Notably, JEC doping resulted in significantly larger nanocrystals compared to undoped samples. XRD patterns, Figure 3a, showed that all samples crystallized into the monoclinic phase of HFOO, consistent with PDF 034-104. Using Rietveld refinement with Profex 5 theory, we confirmed an increase in crystallite size with increasing temperature, which aligns with the particle size data obtained from TMM. Diffuse reflectance spectroscopy, Figure 3b, indicated a band gap range between 545 and 5.52 eV, which is relatively high. Among all samples, the one doped with G-DOT showed the highest absorbance in the ligand-to-metal charge transfer band, which is attributed to energy transitions located in the ultraviolet region of the spectrum. Photoluminescence spectra, Figure 3s, showed characteristic emissions for each lanthanide ion. However, an important trend was observed. As the calcination temperature increased from 800 degrees C to 100 degrees C, the luminescence intensity of UAH and DIG-doped samples decreased. This is likely due to non-radiative relaxation processes or thermal quenching, associated with oxygen vacancies or changes in the local environment of the lanthanide ions. Interestingly, similar behavior has been reported in literature, such as by Rosalba et al., who studied zirconia systems and found a linear correlation between temperature and luminescence, influenced by synthesis conditions and structural vacancies. Conclusions. To summarize, monoclinic HFO nanocrystals doped with GDA were successfully synthesized using a Sol gel method. The particle and crystal sizes increased with thermal treatment, especially in the doped system. Diffuse reflectance data confirmed large band gap values, while photoluminescence analysis revealed decreased emission intensity at higher calcination temperatures, primarily for Youant and DeWatt. These results suggest that dopant type, thermal treatment and synthesis route significantly influence the optical performance of lanthanide-doped HFO materials. Thank you for your attention. If you have any questions or would like to discuss potential applications or collaborations, I would be happy to talk with you.